If we were to connect two 1.5 volt cells in series, what do you think the net voltage that we would measure if we measured the potential difference, the voltage difference between here and here would be? Take a guess. What would make sense? 3 volts, yeah. You can think of it as, instead of having one big 3-volt chairlift, this mountain has 2 smaller chairlifts. You go 1.5 volts up the mountain, you get off, you ski on to the next chairlift, and you go 1.5 volts up the mountain for a total of 3 volts. Okay? I'm not going to do a big song and dance. That kind of makes sense. In many portable appliances, CD players, CD players, once upon a time, we used to listen to music on these silvery rainbow-colored discs called CDs. And so you would put a CD in, and it was amazing. It held 20 songs. 20 songs on one CD! Who would have thought that? It was amazing. And then your CD player would spin it, and that power had to come from somewhere. You would arrange the batteries in your CD player in series so you could stack the voltage. The problem with doing this, though, is that because voltage total went up, but resistance total didn't, total current went up, which means you're bleeding out the batteries faster. The batteries burn out faster, because you now have twice or 4 times as much current flowing through it as otherwise. So a better way to do it would be to connect cells in parallel. What do you think the total voltage running through this resistor is? 3 volts? 1.5, because some of the skiers went up this chairlift and went down. Other skiers went up this chairlift and went down, but the total voltage drop is only 1.5 volts. This circuit, each battery is only supplying half the charge. Each battery will last twice as long. You're going to find, if you look in the back of a lot of electric devices, for example, my graphing calculator, they combine it. 2 of those batteries, each pair is in series to give you a 3 volt and a 3 volt, but by putting 4 batteries in there, instead of having the batteries burn out twice as fast, we get back to where we started from, and that single AAA battery will last for what it usually does. Next time you put batteries into something, you can ask yourself, hey, are these in series, or are these in parallel, or is it a mix match? Rechargeable batteries are charged by connecting them to a cell that forces current back through the cell. So example 3, if we connect a 1.5 volt rechargeable battery to a 6 volt charger, then first of all, which way do you think the current will flow? To the left or to the right? And your hint is, which way is going to be downhill overall? Max? Yeah. The current is going to flow, let's even label it this way. And what you're actually doing is you're forcing current backwards through this battery to recharge it. This is where my ski hill analogy breaks down, because typically you don't ride down a chairlift, but that's sort of what the current is doing. The skiers are riding down the mountain through the chairlift. What do you think the net voltage reading would be right here? What's the voltage drop between right there and right there? 4.5 volts, yep. You gain 6, you lose 4 because you're going against the chairlift. Sorry, you gain 6, you lose 1.5 because you're going against the chairlift. So, in terms of the ski hill analogy, cells in series, like example 1, are like a 2 chairlift ride to the top of the mountain, or a 3 chairlift ride, or a 4 chairlift ride. Those big mag lights, those big massive flashlights, they typically have 4 batteries in series, or 6 batteries in series, or even 8 batteries in series. Well, you need a lot of voltage to get a big bright light, but you're also draining those batteries in a real hurry. Cells in parallel, like example 2, are like 2 chairlifts, both of which lead to the top of the mountain. Opposite cells are like 1 up chairlift followed by 1 down chairlift. And so the key is properly label the circuit. Show which way is downhill. Principles to keep in mind. Positive means higher, negative means lower. Current flows downhill, and if you go from positive to negative, that's downhill. If you go from negative to positive, that means uphill and you gain. So if you're going backwards through a battery, subtract the voltage, don't add the voltage. Meh. 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 This circuit here is actually first-year university. You will not be getting one this tough on your test, but we can totally handle it by skiing and Kirchhoff's rules. In fact, I think we can handle it without even redrawing this puppy. So let's see if I can fill in all the blanks, where the missing eyes are and directions are, and what that mystery resistor on the right is. First thing I'm going to do is I'm going to figure out which way is downhill. How many batteries does this circuit have? Which is the bigger battery? Downhill is this way. Label that. This way. I'm a little not sure on that middle strand whether downhill is that way or I'll leave it blank. But I'm pretty sure that's downhill, that, because that's a ski run that I can do. I can ski that run there. Okay. Now I'm going to go look for anywhere where there is current. Did they tell me current anywhere? No. Where? No. Oh, how many amps right there? How many amps go right there? So let's label that. I know two things, I know three things, and four things. I know the voltage. How many volts do I lose going through that resistor?
12.5.
All right. Let's ski. It does specifically say the current is going this way. They gave me an arrow there. So let's ski this ski run. Let's start at the chairlift. How high? 4 volts. Oh, I can answer this question. I guess the current direction must go that way. How many volts do I lose through this resistor? I don't know. How many volts high did I start, Duncan? Whee! How many volts did I lose going through this resistor? What did I start with? What must I lose going through that resistor? Has to be. Must be. Is that okay? Let's ski a different run. How about that one? How high? Oh, which way is the current going right here? I'm got to be going that way. Whee! Oh, I don't know how high that hill is. Whee! Could that get me to the bottom of this chairlift? So if I lost 2.5 volts there, how many volts must I lose in that resistor? Got to be 3.5. Otherwise, how could I have ended up back to the bottom of the chairlift? 0. Oh! I know two things. What else do I know? Current. How many amps are going through here? How many amps are right here? 1 amp? How many amps are right here? How many amps are exiting that junction? I can fill in this. Oh, first of all, I guess 1 amp, I can fill in that blank. And 1.5 amps, I can fill in that blank. How many amps are going through mystery resistor R? Oh, now I can tell you the resistance. V equals I times R, so R equals V over I. It's going to be 2.5 over 1.5. How many ohms is that resistor?
1.6.
Are there any other blanks that I need to fill in? Told you we can handle it. Homework part 1. No, no, no. 3 is okay. 4 is good. 5 is good. 5, when the switch is open, that 10 ohm isn't part of the circuit. When you close it, the 10 ohm is. I would just solve it. 6 is good. Since it says the bulbs are identical in number 6, and there's a 10 volt battery, I would just give each bulb a resistance. I'd probably use 5 ohms or something like that, or 2 ohms or something like that. 7 is fair game. 8 is fair game. 9 is fair game. 10 is fair game. 10 is probably harder than I would ask on a test. Maybe not. And 11 is fair game. Let's finish off the course. Lesson 7, terminal voltage. Earlier in class, I handed out some batteries. Who remembers what was the voltage stamped on each one? 1.5 volts. You never actually get 1.5 volts when you hook this up. 1.5 volts is the maximum theoretical voltage, but you actually always lose a tiny bit of voltage traveling through the battery itself, because the battery itself has resistance too. We've ignored that up until now, but really in each battery, James, whenever I've done a circuit and had other resistors out, like external resistors, I should also have had a little resistor right by the battery showing actually you lose a tiny bit of voltage going through the battery. So I wrote here this, terminal voltage. This is the voltage potential, the actual voltage between the ends of the battery or cell. So there is a diagram. If you write the circuit diagram, this here, that little funky E, we call the EMF. It's an archaic term. It stands for electromotive force. It's back when they didn't quite know much about what was going on and they thought it was a force. It's a voltage. This is constant. It's printed on the side of the battery. And it is the maximum theoretical voltage. We never actually get it. If you hook up a voltmeter to this, it will say 1.5 volts, but that's because no current is flowing through the battery. As soon as you have current flowing through the battery, you're going to drop. This lowercase r is the internal resistance of the battery. Every battery has some actual resistance. Now we're back in our real physics world, Drake, instead of our magic physics world where everything works so nice. Actually, there is some resistance traveling through this. So, if we have a current coming in, put a little labeled I right there. What's the voltage, what's the terminal voltage right there? How many volts is there? Well, what you're actually getting is the maximum theoretical voltage, that's the chairlift, minus the voltage drop across here. Question? Oh, who else has Timbits? Yeah, we're going to collect. Back here now?
Yeah.
Squirrel. Okay, we're back. Voltage is what times what? So this little voltage drop is calculated by the current flowing through it times that little resistance. This is the actual terminal voltage. That equation is actually on your formula sheet, but I'm going to encourage you to really not take it seriously. It's much easier to just think, you know what? Chairlift. What's this? Well, in terms of my ski hill analogy, you may have noticed if you go skiing, right when you get off the chairlift, don't you ski down a tiny little hill? Little bump? That's what you lose coming off the chairlift. That's really what this internal resistance is like. Sometimes you'll see it put in, to the left by the negative terminal. Sometimes you'll see it put right by the positive terminal, but often you'll see them put a little dotted line around the whole thing to show you that little resistor is part of the battery. It's not actually part of the circuit itself. In which case, if you want to know how many volts you're getting from the battery, the terminal voltage is what we call it. Well, it's what you get from the chairlift minus what you lost going down that tiny little hill. Unfortunately, my analogy breaks down a little bit because depending on the current, the more you lose, which means somehow that hill at the end of the chairlift changes its height, and in real life that doesn't happen. So, okay, the ski hill analogy has carried us a long way. It's got some flaws. Okay? So right here, that's I times little r. This is the EMF. This is what's printed on the side of the battery, your maximum theoretical voltage. But this is the actual voltage you're getting when you hook it up to the circuit. This is the terminal voltage. If you actually, once it's in the circuit, measured the voltage across the battery, you would see, oh, I'm not getting quite 1.5 volts, maybe 1.45, maybe 1.3 volts. Example 1 says, what happens to the cell voltage measured by the voltmeter if we close the switch so that the current drawn by the circuit increases? So, how dark is yours? If you can write on there, I would encourage you to say there's a little tiny resistor and then a battery. That's really what's going on in there. Okay? And that voltmeter right there is measuring the terminal voltage, which is your maximum theoretical voltage minus that little bit you lose going through the battery. And this current here is almost always going to be the total current. The only time it won't be is if we have multiple batteries, and although I've covered it with you, I'm not going to test you on that. So really, what this question is asking is, what happens to the total current when you close the switch? If total current gets bigger, terminal voltage gets smaller. You lose more going through the battery because this number would get bigger. If total current gets smaller, terminal voltage gets bigger. You lose less going through the battery. Oh, if there's no current, like right now with this battery I'm holding in my hand, the terminal voltage will be the maximum EMF. If you put a voltmeter on here right now, you'll measure 1.5 volts. It's just you'll never get that in an actual circuit. Well, when we close the switch, we add a resistor in parallel. Who remembers when you add a resistor in parallel, what happens to your total resistance? Our total, what did you say? Decreases. If our total decreases, what happens to I total? Increases because we're still stuck with V equals I times R. And so, what happens to the terminal voltage? Well, let's even go like this. I times little r increases, because I just increased. And so the terminal voltage gets smaller. You lose more going through the battery when the current goes up. Example 2 says, find an expression for the terminal voltage. The cell supplies energy to the circuit. We already did. We said, you know what? The actual voltage is what's printed on the side of the battery. That value never changes. Minus whatever you lose going through the battery. Let's call this here R1. Let's call this here R2. Let's call this here, anybody? Let's call this voltage 1, voltage 2, and voltage 3. Okay? The terminal voltage will be equivalent to voltage 1 added to voltage 2 added to voltage 3. Basically, the terminal voltage says, look, if you go maximum minus little bump at the end, that's what you have left over for the rest of the circuit. So sometimes, as a shortcut, rather than walking through this, I may say, oh, if that's 5 volts, 6 volts, and 8 volts, that's my terminal voltage. The EMF is this plus this plus this plus this. That gives you the maximum theoretical voltage. The EMF is V1 plus V2 plus V3 plus whatever you lost going through the internal resistor. And again, we're using a lowercase r for the internal resistance, Robbie, to symbolize we want that resistance to be small because we don't want to lose a whole bunch. If it was a massive resistance, you'd have almost no voltage left to power your device. So, Mr. Dewick, why don't we design batteries with no resistance? Because actually, that internal resistance is helpful as well. Example 3. Find the terminal voltage. So either they'll show big dots on either end of the battery, that's meant to represent the battery terminals, or you're going to see on your ultimate review, they'll almost always put a big dotted like that around it. Either way is fine. Rather than use the formula, here's what I would say. What's the EMF of this battery? Okay, and the EMF is equivalent to the chairlift height, 20 volts. What's the total resistance of this circuit? Well, there's 2 resistors. How are those 2 resistors aligned, series or parallel? I would just say, you know what? The total resistance is 30 plus 2, it's 32 ohms. Now we run into a bit of a problem because I've been using VT for total. So the terminal voltage, sorry, before I get there, my bad, let's write it right here. What's the total current? How many amps are flowing through this? 20 divided by 32. Which is what? Sorry? 0.625 units, amps. So I guess the current is flowing this way, this way, this way. I have 0.625 amps here, and through this little internal resistor, I have 0.625 amps. How many volts do I lose going through this little internal resistor? I times R? Yes. By the way, if you haven't, maybe you should just write V equals I times R, just so you have your frame of reference. What was it? 1 point? All terminal voltage is asking, Kayla, is what's the voltage from the bottom of the battery to the top of the battery, including the little internal resistor? So, Kayla, how many volts do we gain? How many volts do we lose? The terminal voltage is going to be 20 minus 1.25. Whatever the heck that is. Bit of a problem. Because I use T for total, I tend to write out V term. What do they use on your formula sheet? Do they use V with a subscription T, or do they use
V terminal.
Oh, they do write V terminal. Okay. It's going to be 20 is what you would get theoretically, but in this case, you lose 1.25. Heck, I can do that in my head. 18.75 volts. That's what's left to power the battery. Sorry, power the circuit, power the external resistor. Don't believe me? Go I times R right here. What do you get? Do it on your calculator. I times R right here. What do you get? Of course you get 18.75 because that's what's left to power that resistor. What I'm really saying is, although there's a formula, Julie, there's really about 3 or 4 different ways just to figure it out using Ohm's law and Kirchhoff's law and skiing. And so I'm reluctant to add yet another formula when I can just figure it out intuitively if I understand what they're asking for. The terminal voltage, it's the difference between there and there. Oh, if they wanted the EMF, that would be just that thing. So then if I wanted that thing, I would add those 2 voltages together. 18.75 plus 1.25 gives me that. It says, find the terminal voltage and the internal resistance. Well, that way is downhill, downhill, downhill. What have they told me in this circuit that's going to make my life really easy? Total current. Question's going to fall apart. How many amps are flowing through this 30 ohm resistor down here? How many volts? I times R? 45 volts. You'll notice that's my only external resistor. I'm telling you, that's the terminal voltage. That's what's left to power the device. What was the EMF of what's printed on the side of my battery? 50. What do I have left over for that external resistor? 45. What must I have lost going through the battery? How many volts did I lose coming off the chairlift? How many amps are going through this internal resistor? Oh, how big is the internal resistance? Well, V equals I times R. I guess R equals V over I. Make sure you use the... Question? Well, I use more nouns. 45? Yeah, I times R. 1.5 times 30, right? 45. Okay? And again, the reason that's the terminal voltage is that's my only external resistor. If I had 2 external resistors, I'd add up both those voltages. Those would be the terminal voltage. That's what I have left over for my circuit. The internal resistance is going to be the voltage drop divided by the current through there. 5 divided by 1.5. How many ohms of resistance is this battery? 3.33? So I would much rather, Sarah, just use what I already know. However, that internal resistance, even though we lose a tiny bit of voltage powering a circuit, it's that internal resistance that allows us to recharge batteries. So, example 5, you can make a little note, is not going to be on your test. I'm not going to give you a 2-battery system, but I'd like to take a couple of minutes to explain to you, A, how we recharge batteries, and B, why it takes so long. So, here is our battery charger, which means this is the larger voltage, so the current is flowing this way. Okay. Now we're recharging the battery, so the current is going this way. The terminal voltage between here and here, the terminal voltage between those 2 points is going to be the maximum EMF, but this time you're going in the opposite direction. So instead of going downhill on that little bump, you're going uphill on that little bump. It's going to be plus that little voltage gain. And it's this tiny little bit of extra voltage. This is what recharges a rechargeable battery. And this explains why we don't have batteries that just recharge really fast. If you wanted it to recharge really fast, you'd have to make this number as big as possible. The only way to do that would be to make this internal resistance huge. That would recharge fast. Oh, but then you'd have almost no voltage left over to run anything. You'd lose almost all your voltage just going through the battery. Can't have it both ways. So we have very little resistance going through the battery because we want to be able to power devices. We want voltage left over to power things. But the trade-off, Drake, is then this number here is going to be really small. You're only getting a little trickle charge going back in the opposite direction to recharge things. Sorry. Yeah?
Do you have a battery with like a double circuit inside it? One with like a very large...
They're coming up with clever workarounds and things, or they're coming up... I know the Samsungs, the most recent Samsung Galaxy and Note series have a quick recharger, which goes faster. I'm willing to bet they do have a secondary circuit or something that they're running through there somehow. I haven't dove into the physics of it, but to me, that makes sense to me. Yeah. Yeah. The Holy Grail would be something that you can both drain quickly and recharge quickly without having a massive resistance. But that would probably be some other type of technology. We're looking for it. So, let's recharge a battery. It says, find the terminal voltage. The cell is being charged. Current is going this way. Okay. First thing. How high? Now we're going in the opposite direction. We lose 9 volts. My first question is, what's the total voltage in this circuit? 21 volts. 30 gain, 9 loss, because we're going backwards through the battery. Downhill, as it were. You okay with that? What's the total resistance in this circuit? All 3 of them are in series. 11. What's the total current flowing through this circuit then? Well, it's going to be V total over R total. It's going to be 21 over 11. 0.909? No, that's not right. It's going to be close to 2. 0.1909. Yeah, there we go. I forgot the 1. Let's call it 1.91 amps. How many amps in this top resistor? How many volts do I lose going through that top resistor? V equals what times what? So 1.91 times 5? 9.54? You're right. And that bottom resistor is identical, so it also has 1.91 amps and 9.55 volts. So I'll just take this number and double it. How many volts did we say grand total were in this circuit? How many volts am I using up in those 2 external resistors? What's left for the little internal resistor in the battery? 1.9, 1.91. Yes? Volts. And what's its resistor? 1 ohm. So I can tell you its current is 1.91 amps. The real question, though, is what would the terminal voltage measure? We're recharging the battery, so this battery, this resistor, this internal resistance isn't losing voltage, it's gaining voltage. We got a 9-volt chairlift plus that. If you measured the voltage across here, the terminal voltage is going to be 9 volts plus 1.91. It's going to be 11.9 volts. And 11.9? 10.9. Is that right? 10.9. That extra 1.9 volts, Robbie, that's what's doing the recharging. Which is why it's not going to recharge very quick. But again, we're stuck with that. We could get this voltage bigger by making this resistance bigger, but then you'd lose a lot more when you plugged it back into the circuit and tried to run anything. So in summary, if the cell is supplying energy, then terminal voltage is EMF takeaway. You lose voltage going through the battery. Thank you. I'll have to fix that. I wasn't consistent. Okay? I mean, I did put it here, but you're right. I'll put a term there instead. If you're recharging, instead of a minus sign, it's a plus. That's why I think on your formula sheet there is a plus or minus. Is that right? I am going to say on your yellow formula sheet, if you want to, you can cross out the plus or minus, and you can just make it a minus. I'm not going to test you on rechargeable batteries, but for what it's worth, I do like to explain why it is that you can't recharge a battery very quickly. You can't have it both ways. It's either going to be a good battery to power stuff with, or it's going to be a great battery to recharge. You can't have one that does both. And we would rather have batteries that are good to power stuff with. We'll just recharge them overnight or whatever it takes. So, if it's being recharged, you can nuke that. Homework. Ultimate take home, ultimate. I'm not going to assign any questions from lesson 7, but there is going to be terminal voltage on your test like crazy. But if you actually look at the ultimate review, I can already tell you at a glance which questions require terminal voltage. I'll show you what I mean. This one does not. This one does. Come on. Nope. By the way, if you don't see an internal resistance, they've already calculated the terminal voltage for you, and you don't need to worry about EMF or any of that stuff. Here, nope, nope, nope. Here, so it's pretty obvious when you'll be using terminal voltage, and you can now do every question on the review. So lesson 6 is great practice because a lot of those circuits are tougher than I'm going to ask you on the test, and then you can start to work your way through here. On Friday, I'm going to give you a take-home quiz. I see you Friday. Yeah. And otherwise, it's going to be work on the review, work on any missing circuitry stuff as well. Would you like to write your circuitry test? We can go on Wednesday. That lets us mark the quiz Monday, and Monday would also be final exam review, work on any other stuff. Wednesday would be circuitry test. I think that's the last class that I see you before the final exam schedule kicks in. Is that right? And so then your final exam would be the following Monday. Or, if you want to, I can give you the take-home quiz Friday. I can post an answer key and a video solution key. You can just mark it yourself on the weekend. You can write the circuitry test on Monday. That would allow us to quickly go through the circuitry test on a Wednesday and do final exam review Wednesday. Those are your options. We're going to vote. You guys are going to decide from either blocks. Who would prefer to write the test next week, Wednesday? Who prefer to write the test next week, Monday? So you'll mark the take-home quiz on your own. So your test will be Monday.